Hey guys, welcome back to Math from my desk. Today I will be discussing differentiation in the context of kinematics. So we know kinematics as the study of motion. Usually when you study kinematics, you do not take into consideration dynamics, which is also a different field within the bigger field of mechanics, within the very bigger field of physics. So calculus very much has a lot of applications in kinematics, mainly through differential and integral calculus. And this video will be focusing on differentiation, so on differential calculus, and relating position, velocity, and acceleration in terms of differential calculus. So let's go ahead and start. So first we know that average velocity is equal to the change in position, also called displacement, so delta x, over delta t, the change in time. And so if you were to graph this, so our y-axis is position and our x-axis is time, and we have a line here. So the average velocity would simply be the slope of the secant line. So the secant line would probably go something like this here. So this formula here gives you the average velocity throughout the entire time interval, or throughout the entire period that which you are calculating the average velocity for. So what if you were to what if you wanted to find the velocity at a specific instant of time? Let's call that instant C. Well, in order to do that, you're gonna take the limit as the change in time approaches zero. So say you have two intervals here, or you hold on, you can see them as these bigger intervals here, this and this. What if you were to shrink these two intervals so much that they will get infinitesimally close to zero, but will never get to zero? This is the definition of a limit. So we want to take the limit as the change in time approaches zero. And essentially, we reach the definition of a derivative. So in order to calculate the instantaneous velocity, which the velocity in this case is the slope of the graph, because change in position here over change in time, then you would have to take the derivative of position with respect to time. So we can write v is equal to, and go down here, dx dt, which represents the derivative of position with respect to time. And so this right here is how you would find the instantaneous velocity. And likewise, we know acceleration, average acceleration at least, is the change in velocity over the change in time. And so if we were to build a similar graph, but instead of position in the y-axis, we would have velocity, and the x-axis we would still have time, and we were to have a line here, this formula would give you the average velocity, so the average acceleration, so the slope of the secant line, which would look something like this. However, if you wanted to find the acceleration at point C, so you want to find it over an infinitesimal period of time, you would have to take the limit as delta t approaches zero, so essentially the derivative. So acceleration, instantaneous acceleration, and what instantaneous means is at a given instant of time. So instantaneous acceleration will be defined as the derivative of velocity with respect to time. And so these two formulas here are the essence of differential calculus in the applications of differential calculus in kinematics. And so if we were to solve a problem here, so let's say we have a particle that's whose position is modeled by a function x of t is equal to, let's say, 3t squared plus, let's say, 4t cubed plus, let's just say, cosine of t. Well, in this case, what would be the velocity of the instantaneous velocity of the particle here at, let's say, t equals 90? So 90 seconds. In order to do that, well, we just define velocity as the derivative of position with respect to time. So we would simply take the derivative of this expression here. So x prime of t and x prime of t is the same thing as dx over dt. These are just different notation. I believe this is the Leibniz notation and this is the Lagrange notation. Newton has a notation, but it's less famous. So I have x prime of t is equal to, so now essentially for here, this is the power rule. So we're gonna multiply 2 by 3, which we get 6t. Then we do 2 minus 1, which is just 1, so we just keep it like this. And same thing here, we have the power rule. So we have 4 times 4 here. Is it 4? Yeah, it's 4. So we have 4 times 4, which is 16. And we have 2 cubed, because 4 minus 1. And I will do a video on different rules of differentiation, whether they are the power rule, product rule, quotient rule, chain rule, constant rule, etc. And I will be doing that soon, and also on integration. So then we reach the the derivative of a cosine here with respect to t, which is just negative sine, so you can just do minus sine of t. And I may do a video proving the derivatives of cosine and sine. And so this function here models a general solution to the velocity. And so all you would have to do to find the instantaneous velocity is plug in your t value, which in this case is 90. So x prime of t is equal to v of t velocity. So let me write it like this. X prime of 90 is equal to v of 90 is equal to, well, we would have to do 6 times 90, which, let's see, 6 times 9 is 54, so we add 0, that would be 540. 540 plus 16t cubed. Okay, this is a very long, it's a very long multiplication, so honestly I'm just going to change this to, let's say, 2 to simplify this. So if you were taking the AP Physics C mechanics exam, you would be able to have access to a calculator. So no matter the seconds here, you could just plug that into your calculator. So here we have 6 times 2, which is 12, plus 16t cubed. 2 cubed is 8. Then we do 16 times 8, which, let's see. So we have 16 times 8. So here we have 48, and then 1 times 8 is 8, plus 4, left with 12. So 12 plus 128 minus sine of 2. And remember, if you were, I don't know about other examinations, but for AP Physics, you would have access to a calculator. And so we can go ahead and simplify this. So 128 plus 12, well, let's see, that just plus in here 38, so that's just 140. So 140 minus sine of 2t, sorry, sine of 2, that is equal to the instantaneous velocity at t equals 2 seconds. And likewise, if you were to take, if you wanted to find the instantaneous acceleration, you would simply find the derivative of velocity with respect to time, which you can see as the second derivative of position with respect to time. So let's go ahead and do that. So we have 60, so let me write, I can write it as x prime of t to simplify the second derivative is equal to v prime of t is equal to acceleration as a function of time. And this is equal to, well, let's see, the power rule. 60, the derivative of 60 is 6. And again, if you're confused by the power rule, I will be doing a video on it soon. And then we have 16 t cubed, which 16 times 3 is, let's see, okay. So I'm just going to use this. I'm very bad at my arithmetic. So 16 times 3, 6 times 3 here, 18. And then 1 times 3, 3 plus 1, 4. So 48. So we have plus 48. And then the derivative of sine is cosine, so we're left with minus cosine. Hold on. I did this wrong here. 48 t squared. And then we have minus cosine of t. So this right here is the general solution for the acceleration modeled by the original function here for position of the particle's motion. So you could plug in 2 here in order to find your total your instantaneous acceleration at t equals 2 seconds. So I hope you guys enjoyed this video where we explored applications of differential calculus in the context of kinematics. I'll be doing a video soon on the applications of integral calculus in context of kinematics, which is essentially the opposite of what we did here. So we know integrals are basically antiderivatives. So since velocity with respect since velocity is the derivative of position with respect to time, position here is going to be the integral of velocity with respect to time, and likewise velocity is going to be the integral of acceleration with respect to time. So I hope you guys enjoyed this video.